So, because of a periodic nature, trig functions are used to model phenomena that occur again and again, something that happens repeatedly. All right. One of the most common places you're going to see that is vibratory or oscillatory motion. Okay, that would be something that just kind of quivers or goes up and down. Um, you think of a guitar string. You think of the pistons in an engine. Okay, those things that just go up and down on that same cycle and the same speed throughout. Okay, here's some of the most common ones you see: guitar string motion, swinging of a pendulum, bobbing of an object attached to a string, radio waves from an FM station, and sound waves from music. Okay, those are all based upon simple harmonic functions. Now, some of those are a little bit different. For instance, a guitar string. So if you pluck it, it vibrates, right? What happens eventually? It's going to stop. All right, it has to do with like air resistance, friction, gravity. Those types of things affect a lot of these things. All right, the ones that are produced by something, such as the FM station or sound waves in music, they're going to be consistent. All right, they're still going to come through. They reverberate through your ears, for instance, if you're using the sound waves. Now they change in octaves and those types of things. Whenever, for instance, music, all right, if it's a higher octave or a lower octave, the sound waves or how far apart the waves are is going to be closer together and farther apart. Closer together is higher pitched, farther apart is going to be lower pitched. Okay, so to start one off, this is probably the most common one you see in math. Obviously, my picture is moving and yours is not, but it'd have been really cool if I could find out if I had a way to make it move on the paper, wouldn't it, Solomon? I know you're a little disappointed right now. Put the slider like tab in the back, and you can shake it up and down. All right. So this diagram below shows the motion of a ball attached to a spring hanging from the ceiling. So if I had a spring hanging up here and I had a ball attached to the end and I pulled it down, what's going to happen when I release it? It's going to go boing, 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 like that. It's going to make that funky noise. All right. But that curve that it follows, again, imagine that it would continue on that same path. All right. We know what happens with the spring. If we pulled out, and each time it would get a little bit smaller, a little bit smaller, a little bit smaller, right? So imagine if you pull it down and then that first cycle is what keeps repeating. That's what it would look like here. Okay. The curve above shows the ball's distance from its rest position. It changes over time. The curve is sinusoidal, and the motion can be described using a cosine or sine function. Right, just that up and down motion over time. Now, obviously, a lot of people get confused on the fact that that ball is just going straight up and down. But when I graph it over time, that's how I get that loop up and down. With me? Okay. All right, so let's flash ahead a little bit. So this is what we call simple harmonic motion. So an object that moves on a coordinate axis in simple harmonic motion, if its distance from the origin d at time t is given by either one of those two things. All right, so d equals a cosine wt, or d equals a sine or wt. In this case, the amplitude is your a, just like when we graphed sine and cosine functions before. Okay, the number in front of it is going to be your amplitude, and that's the maximum displacement of the object from rest point. Rest point. Okay, the period of the motion is going to be 2 pi over w, same as what we did before. Remember before we had it in like A, B, and C? All right, they kind of changed the letters a little bit just to fit harmonic motion. All right, so the period is going to be 2 pi over your w term whenever it's greater than 0, and the period is the time it takes for it to go through one complete cycle. So if I pulled the ball down until the whole way to the bottom, released it, how long does it take that ball to go up and come back down to that point where I released it from? Okay, so you're going to use cosine function if you start by resting at an extreme value, and you're going to use sine if you start by resting at the origin. Same as when we graph sine and cosine. Sine starts at the origin and either goes up or down. Cosine starts either at the top or the bottom. All right. So let's look at an example of this. So we're going to find the equation for an object in simple harmonic motion. So we have a ball on a spring is pulled 4 inches below its rest position and then release. Period of the motion is 6 seconds. Write the equation for the ball's simple harmonic motion. All right, so they pretty much gave us a lot of this stuff already, didn't they? We just kind of have to plug it in. So first off, let's think about this. Okay, so ball's hanging on a spring, right? And then I take it and I pull it 4 inches below rest. That's all the farther down it's ever going to go, right? Is that going to be cosine or sine? It's going to be cosine because it's one of the extreme values, correct? And I pulled it, it's hanging here, I pulled it down to an extreme value. Therefore, it's going to be cosine. So we know that already. But we're just kind of dissecting stuff now. We know it's going to be cosine, and that's because I have it pulled down. All right. Now, let's see. We need to find our A and our W yet, right? A and W. We got to find those two things. Let's find W first. Okay. So W is going to be, that first one's A, I swear. Okay. Our W is going to be our period. Well, we know our period is going to be 2 pi over whatever W is, correct? We know that by definition of the harmonic motion. Okay. Now, does it tell us how long a period lasts? It does. 6 seconds. So we know that this must be equal to 6, correct? Okay, our period by definition is 2 pi over W. We're looking for W, so we know it has to be equal to 6. So let's solve this a little bit. So I'm going to have 2 pi equals 6W, multiply both sides by W. And then we'll divide by 6. So W is going to be pi over 3. With me so far? All right, now we got to, so that gives me my W. To find A, that's my amplitude. Let's think about this. I took the ball from where it was resting at, and I pulled it 4 inches down. So what's my amplitude? 4. It has to be 4. Okay. Now I have everything I need. So D is what, it has to be my distance. All right, so D is, amplitude is 4. We said it was cosine. We said my period was pi over 3. And that's a function of time. There we go. So that graph and that function, that trig function, would represent the movement of that ball over time. Make sense? So what we just did was take our knowledge of sine and cosine functions and graphing those and just apply them to a certain problem. Okay. Any questions? All right, I'm going to give you, I don't know, about 4 or 5 minutes to try this next one. Probably won't even take that long. All right, so I have to find, first off, what type of function it is. Second, what my A is, and then what my W is. Okay, so what type of function is it, first off? Cosine. Why is it cosine? Because you grabbed it and pulled it down before you start the motion, right? Okay, so it's definitely cosine. All right, A is pretty easy. What's my A term here? Has to be 6 because I pulled it 6 inches from rest. All right, and then W, I would have to solve 2 pi over W equals what? 4. You solve that, what do you get? Pi over 2 for W, I agree. All right, therefore, my equation is going to be D equals what? 6 cosine pi over 2t. Actually, I missed something on the last one. It'll affect this one too. So I made one little mistake on this last one. So I grabbed that ball and I pulled it down, right? So what do you think I made the mistake of? Should be negative. That should be negative. And that should make this guy negative as well. Sorry. All right, so that just makes it negative. Because I took it and I started at the negative extrema. All right? All right. So the next type of thing, it's very, very similar as well. Just another way to look at it. So it's a frequency of an object in simple harmonic motion. So in that one, we have the ball in a spring hanging from the ceiling, right? Hold it down, it just kind of goes up and down. In this case, probably the easiest way to look at it is if I took the spring and attached it to the side of this eraser, attached to my hand and erase this eraser, and it kind of goes like this. And one of the places you're going to see that a lot, it would be with like an engine. All right, so the piston's in an engine. Okay, think about it when you're buying a car. What are you talking about? Well, one of the things to talk about is displacement, right? Engine displacement measures the power. You know, it's a way to, it should be a way to measure the power of a car. Well, that's what we're going to talk about here: displacement, frequency, those types of things. All right, so an object in simple harmonic motion given by the same two as before, same exact two things. Now the frequency is basically like the period. Okay, frequency is basically the same, and the same thing. One period is one frequency revolution, essentially. Okay, just a little bit different wording. That's the only thing. It doesn't really change much. All right, so if a mass lies on a smooth surface attached to a spring, mass moves in simple harmonic motion described by D equals 10 cosine of pi over 6t, with t measured in seconds and d in centimeters. So we want to find the maximum displacement. Maximum displacement in this case is my max value. Yeah, my amplitude. It's the same thing. Max displacement is 10. Comes from right there. All right, frequency it occurs at. Same thing as finding our W before, essentially. So my frequency in this case is going to be W over 2 pi. I just flipped it. Okay? So we know that that is going to be right here, pi over 6, right? So I'm going to have pi over 6 over 2 pi. All right? I'm just working reverse order now. Change the wording a little bit. All right, and then if I have that, I have to flip the bottom up, reciprocate it. So I have pi over 6 times 1 over 2 pi. Pi's go away, 1/12. So what does that mean? Well, that means it makes 1/12 oscillations per second. And that's what I just found. It's an oscillating feature. Now, I want to find the time required for one cycle. It's the same as a period. Okay? Or look at it this way. If it takes every 1 second, I make 1/12 of a oscillation or 1/12 of a cycle. How many seconds does it take to make one full cycle? 12. Time required for one cycle? 12 seconds. Boom. That makes sense? So take 12 seconds for one cycle. Anytime you find frequency, just reciprocate it, and that's going to be the time for one cycle. Or if you find the time for 1 cycle, reciprocate it, and that's your frequency. All right, you guys try the last one. Okay, so what's the maximum displacement here? 12. And it would be 12 what? What units? Centimeters. Yep, 12 centimeters. Okay, frequency. Frequency is going to be your pi over 4 over 2 pi, correct? So that's going to equal what? 1/8. What does that mean then? 1/8 what? 1/8 oscillations per second, correct? Good. And then lastly, time required for 1 cycle is 8 seconds. Bless you. Any questions, guys? Say that again.